Good day, my name is Duwan and I'm a senior mechanical engineer at the National Laser Center at the CSIR. I will be giving a presentation about design for additive manufacturing. So the contents of my presentation is I will give an introduction and a background, then I will speak about design for additive manufacturing, the tools, and then part cost impactors, and I will conclude to show or to say where the CSIR comes in. Additive manufacturing is a method of manufacturing parts layer by layer. Improvements to this technology is continuously driving part costs down, but design for additive manufacturing could have a more significant impact on this. The focus of this presentation would be high-speed selective laser melting, and I will give an introduction to some of the design rules and constraints of the technology. Due to the complexity allowed by additive manufacturing, most traditional designers need to change the way that they think. The constraints between traditional subtractive machining and additive manufacturing are almost worlds apart, and this has created an entire new field of design requirements and constraints. So what is design for additive manufacturing? It is a pre-process where a part is modified or adapted to make it more suitable for additive manufacturing while taking into account the limitations of the technology. Powder bed fusion is one of these technologies that uses an energy source to melt the cross-section of a part on a thin metal powder layer. Selective laser melting is a powder bed fusion process and uses a laser as an energy source. The additive manufacturing industry has grown and many companies are investing in the technology. This has caused the popularity of design for additive manufacturing to grow, with many courses being presented around the world. A lot of research has been done on this, with many authors combining vast amounts of research into one paper, like Deagle, Thompson, and Booth. If done correctly, design for additive manufacturing can reduce part costs, build time, and build attempts. And new tools are continuously being developed to assist and improve the design for additive manufacturing process, which could increase the efficiency and drive part costs down. So what is design for? So here's an example of a case study done by Olaf Deagle to show the difference between not going through the design for additive manufacturing process and going through the process. You can see a significant difference between the build times and part costs. So the first tool I would like to speak about for design for additive manufacturing is topology optimization, which is the mathematical approach to determine the load paths within a part under the load conditions where the part will work. Any unnecessary material is removed and only the load-bearing paths remain. This results in a complex, unsmooth organic shape, which is then refined and smoothed before manufacturing. It is a great process to save weight while maintaining mechanical strength within a part. The next tool is build simulation. This is used to simulate a build before attempting it for the first time. It predicts part or support failure, recoater risks, shrink lines, distortion, and so on. It can be used to adjust the support structure design, improve distortion, and reduce the number of build attempts. One also has the ability to export a pre-distorted part. If a pre-distorted part is printed, it will theoretically have distorted in such a way that would make it dimensionally closer to the original design. This is just a picture to show the results from build simulation. And this is a real-life example of where build simulation can be used to predict part failure. You can see there's a crack on the corner, and build simulation could have predicted this crack. The design could have been adjusted and it could have been prevented. Now we'll speak about part cost impact, which will include the highest contributor to part costs, why they have an effect, and how they can be addressed by using rules for design for additive manufacturing. The first one is weight. Any additional weight in a part adds to the build time. It can increase the residual stresses, and this could result in failure. It can be addressed by hollowing parts to reduce the weight, Lattice structures can be used in areas where increased strength is required and would be much lighter than the original design, and thick walls can be pocketed. The next is pre-processing. This entails anything that has to happen before the processing starts. For instance, support structure design, machine preparation, drying of powder, slicing, which happens automatically in some machines, and build simulation. The next is part orientation, which has a significant impact on the build time. Every selective laser melting machine has a wait time, which is when the laser is waiting for the next powder layer to be coated. This means the more layers, the more time is wasted waiting. Parts should be orientated in such a way that requires the lowest amount of layers, but with the least amount of support structures. However, the support structures should still be sufficient enough to keep the part anchored to the base plate. The next is support structures. It is a necessity in any selective laser melting process and serves mainly two purposes: to keep the part anchored to the base plate and dimensionally stable, and to act as a heat sink to conduct heat away from the area being processed. These support structures add to build time and waste material and requires post-processing. The next is build time. It is proven to be the greatest contributor to part costs. This is due to the high cost of machines and asset depreciation that needs to be taken into account when calculating operating costs. This means that machine productivity is vital to profitability. The next one is post-processing. All metal printed parts require some form of post-processing. It entails anything that is done to the part after the removal from the machine and before it is delivered as a finished part. It involves heat treatment or stress relieving, removal from the base plate, support structure removal, surface finishing, and/or machining. So where does the CSIR come in with this? The CSIR with collaboration, the CSIR, originally in collaboration with Aerosud, developed one of the first or the largest selective laser melting machines in the world called AeroSwift, and we also built a proof of concept machine that is capable of the same process parameters. We at the CSIR have access to build simulation software and topology optimization software, and can give access to potential clients so that they do not have to make a large investment. We can also consult and help to design or modify a part to make it more suitable for additive manufacturing, and in turn show how manufacturing industries can benefit from using this technology and prove to them the value of additive manufacturing. Thank you very much, and I will now answer questions.